This presentation will cover the problem of uncertainty for the airline industry after Brexit, using game theoretical analysis in the case where incomplete information is assumed. An evaluation of key literature immediately indicates that there is uncertainty for many industries in the UK after Brexit, due to the limited government transparency on negotiations. This presentation will focus on uncertainty for the airline industry, as airlines depend heavily on EU legislation for productivity gains and expansion. As stated in the literature, airlines have been hit severely by Brexit uncertainty. As the current situation stands for the UK government, EU airlines will lose permission to run flights within the UK and vice versa for UK airlines in the EU. The EU hopes to have a bare bones agreement in place by March the 29th for airlines, but this has not yet materialised. Harsanyi's 1967 Nature game helps to formulate the problem airlines have regarding a lack of information on current EU-UK negotiations. If airlines are equipped with knowledge of probability-based likely outcomes, they can make more informed decisions about their future business operations. We begin with a set of players where n is equal to player 1 and player 2, where the UK is 1 and the EU is 2. Player 1's typeset is defined as T1 is equal to L or S, and player 2's typeset is defined as T2 is equal to S. Here, L denotes a lenient approach to negotiations, where the player will complete a deal, while S denotes strict negotiations, limiting the chance of a deal. We assume player 2 is of type S, as the EU does not wish to grant a lenient deal to the UK and encourage other members to leave. Player 1 has a probability distribution where P is an element between 0 and 1, where P denotes the probability they are of type S, and 1 minus P denotes the probability that they are of type L. We will assume that P is equal to 0.5 to reflect the uncertainty between the two options. Here is an illustration of the normal matrix form of the game that will be used to solve airlines' problem of incomplete information. The numerical values in each matrix are designed as payoffs reflecting the corresponding nature the UK adopts for negotiations, as are those payoffs of player 2, the EU. In the situation where players do not coordinate on the same action, for example, deal, no deal, the assumption is made that hard Brexit goes forward with a bare bones agreement in place. Under the situation of no deal, there will be no agreement covering air travel, the worst outcome for airlines. The best outcome for airlines is a situation of deal, where there is a full comprehensive service agreement in place for air travel. This is the extensive form of the game setup, which enables easier visualization of the probability payoffs. As in the matrix form of the game, we can see that nature determines the L or S chance, again with a probability of 0.5. When it comes to solving the game for the benefit of the airlines, the extensive form shows better possible strategies and outcomes for both the UK and the EU. To calculate the probability-weighted payoffs, as per Harsanyi's method, we are using an example strategy of deal, following the extensive form game as an example, where L nature leads to deal, and S nature also leads to deal. For each player, we will calculate the individual utility payoffs. U1 is equal to 0.5 multiplied by 8 plus 0.5 multiplied by 3 for player 1, and U2 for player 2 is equal to 0.5 multiplied by 6 plus 0.5 multiplied by 5. When we weight these payoffs by probability, U1, U2 is equal to 5.5, which is our overall payoff for this strategy. This calculation method allows the consideration of the probabilities for either of the UK's types and helps to indicate the average payoff and likely outcome of each potential strategy. Following calculation of probability-weighted payoffs for all strategies, as per the method on the previous slide, the resulting Nash equilibria are deal with payoff 5.5, and deal, no deal with payoff 3.5. These can be seen in the diagram on the right, while the left-hand diagram gives a comprehensive visualization of all possible strategy payoffs, weighted for probability, following calculation as per the previous method. Now we can discuss Nash equilibrium solutions. The matrices outlined in the normal form of this game are simple dominant solvable games, with the two probability-weighted Nash equilibria shown on the previous page coordinated on the extreme outcomes, where a deal or a no deal is coordinated on by both players. By reflecting uncertainty through P is equal to 0.5, we settle on the Nash equilibrium that a deal is completed when the UK is lenient and there is no deal when the UK is strict in negotiations, as seen in the payoffs on this slide. So how does this result help airlines if the incomplete information game simply reflects the result of the dominant solvable matrices? The airlines have always known that they will get a deal if the UK is lenient, and may not reach a deal if the UK is strict. However, we have effectively created a model whereby the probabilities specified are adjustable based on new information the airlines receive. For example, if Theresa May were to announce Parliament had agreed on further concessions to the EU, then the UK leniency probability would increase, and airlines could begin tentative preparations, assuming a deal will be in place. However, the closer we get to the 29th of March without concessions, the probability of UK strictness will increase, and airlines should begin to negotiate individual agreements on a country-by-country basis, or consider moving to a headquarters in the EU instead. Thus, despite the simple dominant solvable matrix games used, the incomplete information game may help to inform the business decisions taken by airlines going forward.